And now it's time for the calculus of acceleration. What we're going to do is drop the chalk, watch it go, make some plots, and see how we can understand it in terms of calculus, but just kind of graphical calculus. So here you go, there's the chalk, and there it goes. If I had to draw that experiment, it would look something like this. The chalk is falling down the x-axis, and we're going to consider positive down, and it started at the origin, and down it fell. So I've set up my axes already, but now let's plot the motion. When something is accelerating and dropping, you may have seen it before. It kind of looks like this, kind of like that. All right. And if you think about it, it's accelerating, so the velocity is uniformly increasing. So the velocity time graph should be a line. And if it's under constant acceleration, as something is when it falls, then the acceleration time graph should be a flat line. So there's the three. Now, the idea wasn't to explain why those are the way they are. The idea is to look at the relationships with them, between them with calculus. So we know we can go this way with a derivative. We know that the velocity is the derivative of the position, the time derivative. And you can do it again. You can go from velocity to acceleration. Acceleration is the derivative of the velocity. All these are instantaneous. You can go this way with integrals. All right, so if we're going to go from here to here, we know that the delta x, the displacement that you get here, is equal to the integral from a to b of the velocity dt. Right, this is if the displacement is between the points a and b. And we know you can also do an integral to get from here to here. Here, the change in velocity delta v would be equal to the integral from a to b, a dt. So that's how you could make the changes. Now let's see if you use them, if you get something that makes any sense. Let's look between two times ti and tf. And let's ask ourselves, what is the displacement between those two times? We start at ti initial at some position initial xi. We end up at some final time tf and some final time xf. So we could take those times down and look at those times all the way down to the acceleration graph, like this. And now, let's calculate what we get for this xf minus xi, this delta x. So let's see. We're going to get delta x. Well, we know delta x is x final minus x initial. And according to our calculus rules, let's see, this delta x should be the integral of the v plot. And we know the integral is the area under the curve. So if we want to do sort of a geometric expression or interpretation of this, it would be that area right there. But what is that? That's some, I don't know, some improper rhombus or something like that. So that would be, you don't want to get that area. If you draw a line right here, though, now you're just looking at the area of a right triangle and a rectangle. And since I had geometry in 1984, I think I can still remember how to do that. So let's calculate the area of each of these. The area of the triangle is 1/2 base times height. So 1/2 base, the base is just the delta t, right? Tf minus ti. So 1/2 delta t, and the height of that triangle is what? The height is the difference in velocity, v final minus v initial. So here, this would be v final minus, oh no, I ran out of space. I'm going to call it delta v, like that. So that's that area, but now we have to add this area. So plus, let's see, that area is just length times width. It's just delta t times, that's vi, plus delta t times v initial. Okay, so the difference is just the sum of these two terms right here. Now, delta V was VF minus VI, but we can use this idea again. That difference between final and initial velocity is the area under that curve, because that delta V is equal to the integral of the area curve as a function of time between the 2 points. So it's that area. So we could say then xf minus xi is 1/2 delta t, and the delta V is this area, which is the height A times the base there, delta t. A delta t plus, this one was fine, plus delta t times VI. All right, and now I'd make a quick point something out. I'd say, well, delta t is going to be, say, t final minus t initial. But let's assume t initial is the origin. We always just put that at 0, and let's just call t final t. Let's just say it's the time you're getting to, right? So if we replace those delta t's with just t, from the origin to some time t, then we get the final position is, bring this over here, the initial position plus, that would be v initial times t, right? And that would be plus 1/2 a t squared. And you may recognize that. So if you've done some physics before and kinematics, that's one of the kinematic equations that you memorize. The position that you get is the initial position plus the initial velocity times time plus 1/2 at squared. You memorize this because this is a special case of kinematics. This is true for constant acceleration. So there, I was just showing you, it really just does come from calculus. It comes from applying the basic ideas of calculus and kinematics to the case of constant acceleration. But here I showed you was just sort of a geometrical interpretation. Another important one you can get much more quickly is just that the delta V, VF minus VI, was equal to AT. So if you turn that around a little bit, you can get the other important one, which is that velocity final equals velocity initial plus AT. And you use that one sometimes as well.